In the previous chapter on aldehydes and ketones, we looked at the carbonyl carbon as an electrophile and the oxygen as a potential nucleophile or base. In this chapter, we've looked at the alpha carbon and how that can be deprotonated and turned into a nucleophile. Beginning with the aldol addition reaction, we're going to zoom out and look at this molecule as a whole. That molecule has two parts, and those two parts can fit together like two pieces of a puzzle. Suppose you have an aldehyde in solution. Oops. If you treat it with a base, a strong base like sodium hydroxide, the sodium will go its way in solution and the hydroxide will act as a base. That will rip off one of the alpha hydrogens, as we've seen in previous reactions. It'll attack that hydrogen, the electrons will snap back onto the alpha carbon if you do that proton transfer. And the reason why that hydrogen is acidic, why it's likely to be ripped off, is because the lone pair that is left behind when the H plus leaves, that lone pair is allylic to the pi bond, and so it and its negative charge can be spread out and stabilized through resonance. It's allylic to that pi bond. So there are parallel p orbitals on all three of those atoms that allow the electrons to spread out, and so dilute the charge and stabilize it. Okay, well that's a satisfactory analysis of this alpha position. But you never have just one molecule in a beaker. You often have galaxies worth of molecules. And these enolates of these aldehydes and ketones don't just have one reactive part of the molecule. You have a nucleophile on the alpha position, for sure. That's what we've seen in this chapter. But as we know from a previous chapter, you also have an electrophile on the carbonyl carbon. Well, nucleophiles attack electrophiles, and these are no exceptions. The alpha carbon can attack the alpha carbon of one aldehyde can attack the carbonyl carbon of another. Let's say before it turned into an enolate. The pi bond then could break. The weakest bond breaks. The electrons snap onto the most electronegative place nearby, which is the oxygen. And you can see that we are adding two aldehydes together. So already this name, aldol addition, should make sense a little bit. The addition should make sense. We're adding these two together. So now, if we number these carbons to keep track of them, let's say we have 1, 2, 3, and 4. So 1, 2, and now 3 and 4. On carbon number 3, we'll have an O in oxygen with a full negative charge. So you've added these two together. Now, there is also water in this solution, and that can, as we've seen before, be used to do proton transfers to stabilize charges. And so that negative oxygen there can steal one of those slightly positive hydrogens, the electrons snap back onto the oxygen of water, and effectively what we have in this last step is this here. Okay, so what we have in this scenario is an aldehyde in this purple area, aldehyde, and an alcohol. In other words, what we have is an aldol, an aldehyde and an alcohol that you get by adding two aldehydes together. So that's what the aldol addition is. Anytime you have an aldehyde or a ketone in a solution, although aldehydes do this more efficiently, and that's why they gave their name to the name of the reaction. So the same reaction could happen with a ketone. You would just get much lower yields closer to like 20%. whereas aldehydes will do this give you yields around 75%. When you have an aldehyde or a ketone and just a little bit of catalytic base, you don't need a lot of base. Base is the catalyst. Notice the base that you use at the beginning gets reproduced at the end. Right? When this water loses its H+, you get the hydroxide back. So you don't need a large amount of base. You just need a catalytic amount, so a tiny, tiny amount, because it'll keep getting used or reproduced, and then it can get used over again. When you have a catalytic amount of base, these aldehydes will start sticking together. The alpha carbons will become nucleophiles, and those nucleophiles will attack the carbonyl carbon electrophile on another aldehyde or ketone. And so you get what are called beta-hydroxy aldehydes or ketones. Remember, the carbonyl carbon is the carbonyl carbon. The carbon next to that is the alpha carbon, and the carbon after that is the beta carbon. So you have a beta-hydroxy, an OH on the beta carbon, a beta-hydroxy aldehyde. That's what you get from these Aldol addition reactions. So that's the concept behind these. We're going to think about this reaction, this Aldol addition reaction, from the perspective of synthesis in the next video.